Hi, good afternoon. My name is Mohan Kumar. I'm with Intel. I'm here to talk to you about rack-scale architecture. And first, when I heard about this is my first time at this conference, and when I heard about the conference from Per, I was like, are you sure you want me to talk about platform and hardware and disaggregation? It sounds like a very software-focused conference. He assured me that you're interested in this type of thing. Rack-scale architecture is essentially aimed at, I'm just showing you the abstract to give you a lay of what I want to talk about, which is to essentially look at where the Intel rack-scale architecture is focused on, which is to address the problem that comes today with underutilized and stranded resources in a data center. And to me, the definition of data center is not necessarily something huge and hyperscale. It could be a half rack, one rack, whatever the thing. And the solution to solving this problem is through resource pooling, and I'll talk to you a little bit at that. And I'll talk to you about how the concept of the pool system and how in disaggregating of compute, what you call motherboard virtualization. It's a cool name. I'm going to steal that from you. Given that there is a limited time, I wanted to take one example, which is essentially PCIe-based storage. And I'm taking that because that's the high-performance storage that's used in a compute environment or even a storage environment today, and show you how that resource is disaggregated and then composed back into the system. And then, of course, nothing comes for free. Once you do this kind of stuff, there is implications to that. And as platform architects, we are in an interesting place because we have to almost take a leap of faith and put the hardware in, and the software ends up following to that trend to some extent, because there are some things that work and some things don't work, and I'll also want to talk to you about that in the next one. I'll figure it out. So first of all, if you take any IT environment, the utilization of the data center is not at 100%. It's probably less than 50% in general, in the way servers are utilized. And this is not just about compute. And what happens is that there is inherently storage, memory, everything that's attached to it. And all of those resources, if your server is in use, they get used. If your server is not in use, those resources are essentially stranded resources. Couple that with the trend that you've kind of heard throughout this conference, which is all of you have talked about the data explosion. So data basically doubles every 18 months, right? At that rate, there has to be some way to handle all this data. And what you need is also a mechanism through which there has to be agility to this, the way we bring up this services and service. This has been a theme during this day's session, at least, that when you want to bring on a services, it can take weeks or months, which is what we are kind of used to. We need to be able to get the service up and running quickly. And that I say that as somebody who's privileged for me, when I need a new service, I just go into my lab and as an Intel server person, bring up the servers. But even that is not a minutes proposition. So I also look with envy to the folks that are able to push a button and have the service up and running. And we are getting there, and this is in order to get there fully is really the business need for where we need to go, right? So every IT, Per talked about the OpEx versus CapEx. Regardless of which space you fall into, what do they want? They want both those costs to be done. They want services up in minutes. They want to be able to do real-time analytics on the data that they have at any given point, right? And they want to scale without disruption. One of the big things that the hyperscale folks did for us is this concept of scaling without disruption, right? Previously, you bought yourself a SAN or a NAS or whatever it is, and it has a capacity of X. And when your environment exceeded that X, the process of adding more capability into that was not an easy proposition, right? It involved downtime and all kinds of stuff, right? But what hyperscale solved for us was the ability to go in and say, okay, let's take Hadoop, right? You want one more? Here, bring in another data node. It's up, and now it's part of your infrastructure. And that capability is required if you're going to deal with the data challenges that we're going to face in the future. So no surprise, today, you you get a platform, it's pre-configured for you. It comes with a label, whatever it is from. And if you want to upgrade, like I said, for like a NAS or a SAN, you upgrade the entire thing as a system. That essentially limits what you can do at any given point. And also, it's not very agile if you do it that way. But instead, what folks want is they want everything in your infrastructure to become a service. They want it, Benny said electricity, that's a good example, right? They want everything to be like electricity. It's a service, it's a utility service is what they want. And they want it to be where, oh, I'm lacking more, I need more compute, I add more compute. I want more storage, I want to add more storage. And they want to be able to grow that as they go along rather than buy as you go model, essentially, right? And you want the resources to be tuned to your application workload. This is the reason for the standard resources comes from really this, because either you're oversized or undersized for whatever application that you're running, right? Whereas if you think about the same thing when you go to an, Amazon or Azure and purchasing a VM, you say, I want this amount of core performance, this amount of memory, and this amount of storage, done, right? And that's where we need to get to where the resources essentially, and then as your resource needs grow because your workload is scaling, because you buy the workload, you have some data, and the data keeps growing. And as the data grows, you need to scale your application workload. And then the resources of your platform need to grow along with you. When you do that, what happens is all the things that were essentially dedicated appliances in the IT in the past, I mean, if you think of a SAN, NAS, a network appliance, telco appliance, everything that had an appliance to its title in some way, turns into something that's more a pool of resources, right? And the picture that you're seeing on the right-hand side, by the way, is an Intel rack scale development vehicle. And the things that you're seeing is it's a pool of compute resources. It's a pool of storage resources and networking resources. And then you pick and choose what you want through software definition. And that's what ends up being called in the industry as software-defined infrastructure. So now getting to rack scale itself, so how do we do that? In our case, the way we do that is to essentially exactly that, is to take these resources that are compute, network, and storage, and essentially say, let's treat them as pools. And that means you disaggregate the resources. So if you think of a traditional server, you all have known a pizza box server model. It's got a chassis, it's got a motherboard, it's got CPUs, it's got memory, it's got drives. It may have some SSDs that are PCIe attached. It has a power supply and fans, right? In the concept of pooling, what happens is that if you're viewing these resources at a rack level or at a rack scale, then these resources get disaggregated. I don't need a power supply when I'm building something that at this level, right? You just have one disaggregated one that's commonly supplying power to these things. And I don't even need the storage that is locally attached to me because I have the ability to compose the storage that's required for you at will to the platform, right? And then, of course, the other key thing is interoperability. In order to do the interoperability, you need to have the single pane of glass management. Otherwise, as Per mentioned in his talk, you end up with a vendor lock-in type issues where you have 10 different consoles and you got to figure out which console to use for which, whether it's networking, whether it's storage, whether it's compute, right? You want to get to a point where it's single pane of glass and you have that. So those are the three problems that we are aiming to solve with our architecture here. And how do we do that? And essentially, first we go create the pools, the compute pool, the pool of storage here, and then network fabric is Ethernet here, and then and solve this for scale. Essentially, not focus on a single server or even a rack, but focus on multiple racks. Basically, being able to, and the focus, when I say focus, I mean the ability to essentially manage these things. So when you add one more element into your existing rack, it seamlessly integrates. If you roll in another rack, it seamlessly integrates into your environment. You don't have to do anything special to make these things work together. And that's the promise of, so the pool system, the network management, being able to have a pod-wide storage that goes across multiple racks or servers in there, and being able to assign those things, those storage resources to compute nodes as you need them, and being able to manage all of them, right? So those are the 4 big elements that we are addressing in the rack scale architecture. So briefly on the management framework. So what we do is we take all the things that are the compute, storage, the rack level stuff. So as you disaggregate the elements in the rack, you have a common rack management that has the power and thermals and stuff like that, and then the networking. And we basically standardize this interface through industry bodies to have this management be a common management layer for how you manage these pool of resources. And then Pod Manager is essentially a hardware resource aggregator, if you will, that aggregates resources across a bunch of these things up to a bunch of racks at 10 to 12 racks in an environment. And that then gets exposed to an orchestration layer where the actual workload comes in and says, I want, whether it's a VM or a physical application that comes in and says, I want to run on a machine with this amount of compute power and this amount of memory. That happens at the orchestration layer. So what you're doing, and a few things have to happen in here. So a classic example is the way things like Hadoop work, right? Rather than the way they overcame the problem of moving from enterprise style storage to a cloud-like storage is to they replicate the data. They replicate the writes into multiple places. But replicating, that gives you higher availability because you're not dependent on failure of one storage device to impacting you. And also it increases your read performance as well because you have many places to go to get your data. But the problem we face is how do you know where to write? And in order for you to know where to write, you need to know where those resources are. Otherwise, you may say, I'm making 10 copies, but all 10 copies are to the machine behind a single power supply. It did you no good at the end of the day, even though from a software standpoint, technically you're right, you made multiple copies, but you made all the multiple copies in the single failure domain. So in order to avoid that through this set of management framework, what we also do is to expose the location. It's not a location essentially says here, it's really a failure domain. Expose the failure domain up to software. So when they assign the resources, they assign it in such a way that things that need to have higher availability end up in multiple failure domains. And of course, at the top level also, we have the pooling and disaggregation has little value if you don't have some mechanism on top to say, I need to compose this back and create a system on demand. And that's the composability API, which also we have developed and are in the process of standardizing as well. So just to give you a quick view of what does it look like when you actually end up doing it. So what you see here is a Xeon-based platform. Each one of them is an independent Xeon-based platform. There is no storage here, and there is not even a network here. So everything here has been disaggregated out to various portions inside the rack. So this is similarly, this is the microserver-based platforms. Each one of those blades is an independent server, essentially. And on the other, so and I'll show you the pooled NVM piece in a second. And this is the storage devices, and you put a bunch of storage, and you can attach any storage head node to this bunch of storage, whether it's a hard drives or high performance storage. So what this allows you to do is a model where it does change the model that you use for serviceability, because now you can let these resources fail in place, and you can somebody in the IT decides after how many failures are they going to go deal with these problems. But if you wanted to build a higher availability model, it also lets you build these things in a software-defined manner. So now I want to get into the concept of pooling. These slides are, what happened here? These are not the, is it the right version? Give me 1 second. Did the version I uploaded to Bridget make it here? Maybe not. Okay, I'll just talk to. I'll just talk to it. So before I talk about the value for disaggregation and value for pooling, we need to talk about why would you do that, right? So on the left-hand side, I had some pictures that disappeared. My apologies. On the left-hand side, if you have a server and you had a drive, let's say it's a terabyte. If your server is exactly using a terabyte, obviously there is no point in you disaggregating that drive. The pooling has really no value. If your server uses half a terabyte, now you have standard resources. There is half a terabyte that nobody is using there. So that's the left-hand side of the picture. The right-hand side of the picture is that if a server maybe one day uses a terabyte and another day uses 3 terabytes, again, you don't building a server with built-in storage is not really going to help you, right? You would rather have a pool storage where you can assign that capacity on demand. Right. This is strange. So the way we do this in the rack scale architecture is what we call the pooled NVMe controller. What it is that it takes your, I'm showing the drives as if they are PCIe devices, but that's what they are these days, especially when you talk about SSDs, especially the high-performance SSDs. You take those drives that typically attach to your server, and you disaggregate them into an I/O chassis, right? I think Pur made this comment that JBOD is cool again. JBOF is cool again. Just a bunch of flash, right? So you put the drives in this I/O chassis, and then these connections actually, so if you're trying to draw a line, the line would be right there on top of this thing. That would be where the I/O chassis separates from the server nodes. Now, from the server nodes here, I'm showing you a solution that's connected by PCIe. And on demand, you can essentially say, I want to take drive 1 and assign it to server 1. I want to take drive 2 and assign it to server 10. And you can change those assignments at any time you want. And even though I'm showing a concept here for drives, you can do the same thing with any PCI attached devices. You can do this with FPGAs. You can even do this with NICs if you wanted to, right? And to the point I was making in the previous slide, you can also have capacity where instead of taking the entire drive and assigning it to one person who doesn't need it, you can take partial capacities and assign it to them. And that way, you're doing the same thing that a VM would have done, for example, in a software sense, except that think of it as hardware virtualization in that sense. What this does is not only it avoids standard resources in a data center, but it also allows you to overcome single points of failure. Because if the node was attached to if the drive was attached to a server and it failed, you're just out of luck as far as the data that was on the drive. Whereas in this kind of a concept, you can always assign the drive to a different host and fail over from there. And it also enables you to do a better job of workload migration. We talked about, I think it was you who talked about when we run out of Amazon or any cloud solution says, oh, I'm going to take your workload and move you over there. But if all I'm doing is a compute job, that's an easy thing to do. But if I have storage attached to it that is acting as my caching layer, how are you going to move my caching layer across? And this allows you to do something like that. The same thing that I showed with the PCIe, you can do it. PCIe, the problem with PCIe, for those of you who are familiar with the details of the hardware, is radix. You cannot go a long distances. You need to have repeaters and so on, which adds to the expense. So the natural question to ask is that, why don't I do the exact same thing, but I want something that's a higher radix than what locally within a rack. So I want to go multiple racks and be able to share my storage or any device, my I/O device, for example. And that's done through something called NVMe over Fabric. What it does is essentially takes the storage protocol, the NVMe protocol, essentially that's used by many of these devices, and packetizes it over any fabric. And in our case, in this example, the fabric happens to be Ethernet, but technically, again, nothing stops you from doing it on any other fabric either. Now, in addition to all the benefits that we talked about in terms of disaggregation and standing resources and everything. You also get to have the ability to do this across a much broader radix of your data center. So now, I wanted to do a quick compare of what happens, right? So essentially, if you have the local versus pool resources, your device attachment capacity, essentially, if it's local to your node, you're always limited by whatever you have in your. It's volumetrics that decides. If your server box is 1U and you have the ability to plug in one PCI card in there, that's the capacity you get. And in fact, it may be even worse than that, because that one card may have a limitation on how much power it's able to sink, right? And that will determine how big a capacity drive you can supply. Whereas the pool resource essentially is unconstrained by those volumetrics. And we already talked about the failure domain, which is, if the node fails, it's going to take all the I/O devices with it. Whereas if you disaggregate it, your failure domain shifts to the fabric itself. As long as you keep the fabric up and running through redundancy, you're in good shape on that. And the utilization goes up with the pool resource because you're not leaving anything stranded, because you can always do fractional or full assignments of these resources across much higher radix of compute resources in your data center. And the latency, this is the one place where you do, nothing comes for free. This is engineering, unfortunately, right? So you do incur an additional pooling penalty for the fabric that you're going to pool through. If it's a PCIe, it's in the order of hundreds of nanoseconds. It's probably in the orders of tens of microseconds, or less than tens of microseconds, I should say, in the average case for an Ethernet-based pooling environment. So again, compared to the order of the devices, the penalty is reasonable in terms of what the value it brings in here. And you get to have higher radix. And above all, a lot of folks ask about, why do we do that? And to first comment on JBOD is cool again, one of the things that made JBOD interesting was its division of labor. What it did was, instead of having a drive for every compute node that I have to go meddle with, pull the tray out, put the server out, look at the drive, and replace it and manage it, I have an I/O chassis that's dedicated, that's designed specifically for that purpose. So everything is front accessible. I can go replace the drive at will. So the lifecycle management and refresh cycles of these devices basically got decoupled from the server itself. And so essentially it's component-based management as opposed to the node-based management that model that we have today. That's the other benefit that it brings, and that's really the key benefit for why disaggregation is interesting and why things like JBOFs are interesting for us to look at again. So having done this disaggregation and pooling, now the next step is to compose, right? So somebody comes in and says, I have a workload that needs 2 NVMe drives of 1 terabyte each. Okay, I compose the system and give it to you. And then on the return path, when the composed workloads needs are done, I release the systems back into the pool for the next person to compose. Sounds great, sounds awesome, but there's a problem, right? The problem is that, first of all, you need to know the orchestration layer itself needs to understand the composition capability. This is something that we are working actively with all the orchestration vendors to make sure the orchestration layer in turn understands the location-aware placement and location-aware storage, and does the right thing in terms of how it organizes the workload across the resources. Now, if you go to the next layer, so there is a OS or a VMM, and then there is actually the software that runs on top of it, right? And as a capacity planning, right, I wanted to come in and say, today I'm going to run a specific set of Hadoop workloads, and I want to construct the data center that's optimally suited for it. I can do that through this mechanism. The next logical step would be to say, I'm running this storage app, and it's running out of, it's having a performance bottleneck. It will benefit by having a high performance storage assigned to it, for example, or it'll benefit. I can assign a compute and add it to the list. But if there's a pre-existing resource and I add another device, from a hardware sense, I can always, through hot plug mechanism, introduce another drive into the mix or another FPGA into the mix. But what happens after that? The software today is not capable of taking that and taking it to the next step of saying, oh, I found this resource and I'm going to integrate this as part of my solution. That part does not exist today. But the optimistic view is that this is yet another software follows the hardware. So the capability exists, and hopefully the software will follow the capability to get there. So essentially, through this architecture, the idea is to get to a point where we have, user defines what performance and what performance they need, and get the solution that they need, rather than, you're stuck with what you have. And basically, what we want is to get to a point where it's you get to a point even within your own IT environment. It's buy what you need and use what you buy type solutions. Thank you very much. I think your time is up.